Our next two examples are going to deal with slightly more complicated functions. So in this function you can see this f of x is 3x minus 1 over x squared minus 1. We want to write this as a power series centered at x equals 0. Notice that this is a quadratic denominator, and really to write them in terms of power series we want them to be linear denominators. So I'm going to use partial fractions to write this function as the sum of two rational expressions with linear denominators. All right, so just as a review, when I'm dealing with partial fractions, a kind of a quick way to do it is the cover-up method. So I factor that denominator, and then if I want to know the denominator or the numerator that goes with the x minus 1 term, I can't cover up the x minus 1 term and evaluate the rest of the rational expression for x equals 1. So I get 3 minus 1 is 2 over 2, so that's 1. I get a 1 there. And then if I want to know the numerator that goes with the x plus 1 term, I cover over the x plus 1 term and evaluate the rest of the expression when I let x equal negative 1. And for that I would get a 2. And I get negative 4 over negative 2. Get a 2 for that numerator. Right. So then I take each one of these, each term now, and write a power series for each one of those. Right. So for 2 over x plus 1, I rewrite it as 1 plus x, and it's 1 minus negative x. So my a is 2 and my r is negative x. And for the 1 over x minus 1, I can rewrite that as 1 over negative 1 plus x, and then multiply numerator denominator by a negative, and I get negative 1 over 1 minus x. So I have a is negative 1 and my r is x. If we look at the radii of convergence, they're both 1. And so that function f of x can be represented by the sum of those two power series. So I have 2 times negative 1 to the n, x to the n, and I have negative 1 times x to the n. So I've kept the x to the n term here, and I've collected up the sort of the coefficient terms, 2 times negative 1 to the n minus 1. And then this would look something like this. The first few terms would look like that. All right. So we have this power series now, and the interval of convergence is from negative 1 to 1. All right. So when you sum up two series, the new interval of convergence is the intersection of the original two intervals of convergence. All right. So it's the intersection of the two, and that'll give you the interval of convergence for the sum itself. We also mentioned that at the end of a previous set of notes, we just quickly touched on the idea that if we take the derivative or the antiderivative of a power series, then the radius of convergence remains the same, but the interval of convergence may change. In other words, the behavior at those endpoints may change. So this is an example of getting a power series for ln of x, and we're going to use integration to arrive there, right? So we want to get a power series for natural log of x centered at x equals 1. So we anticipate we're going to have x minus 1 terms, right? From example 3, we found that 1 over x could be represented as this power series. Right, that was also centered at x equals 1. So we need to make sure that they're centered at the same place, right, when we do this. So we found that 1 over x could be represented as this power series centered at x equals 1. Right, and we know that if we integrate or find the antiderivative of 1 over x, we will get natural log. All right, so we can integrate that series And all we're really doing is adding 1 to the exponent of x minus 1 and dividing by the new exponent. The negative 1's all stay the same. They're just coefficients, right? And we have some c when we find an indefinite integral. So if we let x equal 1, we can find that c is equal to 0. All right, because now we're saying ln of x equals this, and if we let x equal 1, this entire term goes away. Natural log of 1 is 0, so c has to be 0. So our natural log of x centered at x equals 1, that power series will look like this. All right, we have the same radius of convergence. So for our 1 over x example, we had radius of convergence of 1. And our interval of convergence, because it was just a geometric series, was an open interval from 0 to 2. Right? We can show here that the interval of convergence has changed. Even though the radius of convergence remains the same, we're now actually going to get convergence at x equals 2. And I'll talk about that real briefly. So when x equals 0, we're going to get this series. So I've factored out a negative 1 to the n. Here I have negative 1. Here's, I'm sorry, no, this is just negative 1 to the n, negative 1 to the n. And then I've broken this negative 1 to the n plus 1 up into negative 1 to the n times negative 1. Right. Now, this negative 1 doesn't have an n involved at all, so I can bring it out in front of the summation because it doesn't depend on n at all. So I have this. Now, this is just negative 1 times negative 1 to the n, to get 1 over n, which is just 1. And that denominator is n plus 1. Right, and so we can rewrite that as a new series starting with n equals 1 rather than starting with n equals 0. Right. Another way we could do that is if we looked at this series here, we would say, okay, that is going to be less than a divergent p-series, so the direct comparison test would be inconclusive. So we could use the limit comparison test and find that it diverges by a limit comparison with a divergent p-series. So when x equals 2, though, we get negative 1 to the n times 1 to the n plus 1 over n plus 1. All right, and we can simplify that out to negative 1 to the n times 1 over n plus 1. So now we're left with an alternating series. And this series converges, typo there, this series converges by the alternating series test. Right? Our terms alternate in sign, and they have decreasing magnitudes whose limit approaches 0. All right, so that's just one example of how that radius of convergence can or will remain the same when we differentiate or integrate, but the interval of convergence may change. In other words, the behavior at those endpoints may change.